In this section, we're going to talk about probabilities for multiple events, events that happen in succession. And to do that, we're going to create what's called a probability tree. This is for sections 7.3 and 7.4. The formula that we use is a product rule. The probability that E and F will happen together is the probability that E happened, and then you multiply by the probability that F is going to happen given that E happened. Now, there's a thing called independent events, and again, this is not a stats class and it's not a probability class. So I'm going a little bit lighter on the notation. The standard math notation is this. Probability of F given is that vertical line that E happened. I just write F given E, but the Watch It guy might use this notation. Okay, so we're going to roll a die twice, so we have multiple events. We have the first roll and the second roll. Find the probability that the first roll is a 4, so that's going to be our first event is E, is that I get a 4, and my second event, we'll call it F, is that I get something less than 3. Okay, so the probability of E happening, so I get a 4 on the first roll, and then F happens, I get something less than 3. Probability that E happens. What's the probability I'm going to roll a 4? Well, there's one way to roll a 4 out of 6 possible outcomes on a die. And then I'll multiply that by what's the probability that the second roll will be less than 3? I could get a 2 or a 1, because it didn't say less than or equal, just less than. So that would be 2 out of 6. You multiply those together, so the probability of those two things happening together is 2 out of 36 or 1 out of 18. Now this is a good example to talk again about decimals. So the decimal probability is 0.05555, and then those repeat forever. So unless the problem specifically says to round it to a certain number of decimal places, don't try to put a repeating decimal in. It's not exact. Use the fraction instead. And it doesn't have to be simplified. Okay, let's try this again. Suppose we have a box and it has 5 white balls and 2 red balls. And 2 balls are going to be drawn from that box one at a time. So there's a first ball and a second ball, but the first ball isn't going to be replaced before we draw the second ball. Find the probability that both balls are red. Okay, then this would be event E would be the probability that you get a red on the first. Then we multiply that by the probability you get a red on the second draw. So the probability of getting a red on the first draw, there's 2 successes out of a total of 7 balls in the box, times by, okay, now, given that we got a red on the first draw, and given that we don't replace it, one of those is not there anymore. So now what's the probability that we get a red on the second draw? Well, now there's only 1 success left, and there's only 6 balls left in the box. So I multiply those probabilities together, that'll be 2 out of 42. Also known as 1 out of 21. And again, that doesn't make a nice decimal, so leave it in fraction form. Let's try it again. We've got the same box with the same distribution in it. What's the probability that the first ball is white and that the second ball is red? So the first ball being white, I've got 5 successes out of a total of 7 balls, and I chose a white ball the first time and it was not replaced. So this is now the situation for the second draw. What's the probability the second is red? Is 2 out of the remaining 6 balls. That makes 10 out of 42 or 5 of 21. Okay, next. The probability of winning a certain game is 1 out of 5. 2 games are played. Find the probability the first game is won and the second game is lost. So I want the probability the first game is won is 1 out of 5. Now, does the outcome of the first game affect the outcome of the second game? Generally, no. Those would be independent events. So what's the probability that I would lose the second game? Well, if I don't win, if I only win 1 out of 5 times, then the probability of losing is the other 4 out of 5 times. Multiply those together, and the probability of winning the first game and losing the second game is 4 out of 25. Same game, and we're still going to play 2 games, but now find the probability that we're going to lose at least one of the games. Okay, I'm going to make a probability tree for this. Comes time to play the first game, and there are 2 possible outcomes. You can either lose or you can win. Now you're going to play the second game, and you can either lose or you can win. Second game, either lose or win. So we have here a probability tree. And on each branch, I'm going to put the probability of that branch happening. So the probability of losing, that's 4 out of 5. Probability of winning is 1 out of 5. Then when you get to the second game, probability of losing is still 4 out of 5. Probability of winning, 1 out of 5. And label each one of these branches. Okay, now we're going to follow each branch. The first branch results in lose, lose, and that probability is found by applying the multiplication property. So 4/5, the probability of the first event times 4/5. So 16 out of 25 times you'll lose both games. Second branch, lose, win. Lose the first, win the second. That's 4/5 times 1/5. If you multiply the probabilities together, that's 4 out of 25. So far we've accounted for 20 out of 25 ways that those 2 games could be played. This branch, a win followed by a loss. A win is 1 out of 5, a loss is 4 out of 5. Multiplying those together, 4 out of 25. And finally, a win-win. If you're going to win both games, that probability is 1/5 times 1/5, 1 out of 25. So if you add those all together, you should have 25 out of 25. You should be looking at 100% of your sample space. Okay. Find the probability of losing at least one of the games. Well, that's here, loss, loss, loss. It's these 3 added together. That adds up to 24 out of 25. Or you could say losing at least one game is the complement of winning both games. So if you win both games 1 out of 25 times, then you would lose a game the other 24 out of 25 times. Okay, let's look at a business-related application. Polk's department store has observed that 80% of its charge accounts have men's names on them, 16% of the accounts with men's names have been delinquent at least once, and 5% of the accounts with women's names on them have been delinquent at least once. What's the probability that an account selected at random is in a man's name and it's delinquent? Okay, here comes our probability tree. We have 2 things going on. One is that it could be in a man's name or a woman's name. And then if it's in a man's name, that happens 80% of the time, which means that the rest of the time, the other 20% of the time, the account is in a woman's name. Now, given that it's in a man's name, what's the probability that it's delinquent? That is 16% of the time, which would mean it's not delinquent the other 84% of the time. If it's in a woman's name, it could either be delinquent or not delinquent. 5% of the accounts with women's names on them have been delinquent, so the other 95% are not. Okay, so here's an example of probabilities changing depending on the first outcome. So the probability for a woman was different than a probability for a man. So part A, what's the probability that it's in a man's name and it's delinquent? So in a man's name and delinquent. 80% chance it's in a man's name, and then given it's in a man's name, a 16% chance that it's delinquent. Multiplying those together, I get 0.128, so that would be about 13% of the accounts. Probability that it's in a woman's name and it's delinquent. So woman and then delinquent. 20% times 5% is 0.02. 1. So much lower probability because there were far fewer accounts that were in women's names. So the sample space for this event would be a man and delinquent, man not delinquent, that's these two branches, and then a woman is on the account and it's delinquent, a woman is on the account and it's not delinquent. So there's only 4 outcomes in this sample space, and each outcome has a probability that's found by multiplying the probabilities on the branches. So this was 0.128, a man and not delinquent, 0.672. 0.2 times 0.05, probability for a woman's account being delinquent, 0.01, and then a woman's account not delinquent is 0.19. And if you add up all of these probabilities, you should get 1.00. That should be 100% of the sample space. Let's look at a couple of homework problems now. A box has 6 red balls, 4 white balls, and 10 black balls. 2 balls are drawn at random from the box, and then this is super important, with replacement of the first ball before the second ball is drawn, so that you're always drawing from a box that always has 6 red, always has 4 white, always has 10 black. What's the probability of getting a red ball on the first draw and a white ball on the second? Okay. Probability of red is 6 out of, that's 10, 20. And then you put the red ball back in, and then you draw again. Probability of white is 4 out of 20. Multiply that together, that's 24 out of 400. Now let's go back and do that part A again, but this time the ball is going to not be replaced before we draw the second ball. So I want probability of red, and then probability of white given that red happened. Probability of red is still 6 out of 20. But now, since that ball is not replaced, the outcome of the first event affects the probability for the second event, because now even though I still have 4 white balls, now there are only 19 balls left in the box. So now it's 4 out of 19 instead of 4 out of 20. So the probability is 24 out of 380 instead of 24 out of 400. Since the ball was replaced, the events in part A are independent because the outcome of the first draw didn't affect the second draw because we put the ball back in the box. But not replacing the first ball changed the sample space, so in part B, the events are not independent, which means they are dependent. Okay, let's try this again. This time let's draw 3 balls, and there will be no replacement. I want to know the probability of white, white, and then black. Okay, so the first probability of a white would be 4 out of 20. Now if there's no replacement, then my sample space changes after that first outcome. Now the probability of the next ball being white is 3 white balls that remain out of 19 balls that remain in the box. Now I've chosen another white. Probability of black, there's 10 blacks out of 18 that remain. So multiplying this all together is 120 out of 6,840. My guess is that at this point in WebAssign, you would be asked to input this probability as a decimal, but then you'd be told to round. So let's say that we're going to round to 4 decimal places. Just read your question carefully to see how many decimal places it wants. 1, 2, 3, 4 would be right here, so the 4 would not cause it to round up. So the probability is 0.0175, about 1 3/4% of the time. In this problem, we're testing shotgun shells, and we're going to fire 5 of them. What's the probability that all 5 will fire properly? So this is now 5 different events happening, and they would be independent. So we're assuming that the outcome of the first shell shot doesn't affect what happens on the second. 10% of the company's shells are actually defective. So the probability of defective is 10%, which means the probability that it's not defective is the other 90%, because those are the only two possible outcomes for a single shot. Either it fired or it didn't. Now I want 5 of those trials, so I'm going to apply this multiplication property 5 times. What's the probability that all 5 will fire properly? Okay, for the first shot, it fires properly. There's a 90% chance of that. Then you get to the second, it also fires properly, and so on for all 5 independent events. Now mathematically we could write that as 0.9 raised to the 5th. That's 0.59049. Let's round it to 4 places. That would be 0.5905. So there's a 59% chance that if you fired 5 of them in succession, that all 5 would work. Now knowing that, I want to talk about complements. We're like, what's the opposite of all 5 of them firing correctly? Well, the complement of all 5 firing correctly is that one of the 5 did not fire correctly. So it's not all 5 have to misfire. So the complement would be at least one will misfire. Now it could have been any one of the 5 shots, and there could have been 2 of them misfire, or 3 of them misfire, or 4 of them. That becomes pretty complicated if you try to work it out in that way. But if you think of it as a complement, if 59% of the time all 5 of them are good, then the complement is 100%, take away the 0.5905, which is 0.4095. So watch out for this at least one. At least one misfire is the complement of all 5 firing correctly. In the homework you will use probability trees, and you'll also use complements to find probability. I want to talk to you about what's called conditional probability, and it uses the word given. Let me go back to the first example that we did. Okay, let's go back to our department store problem again. 80% of the charge accounts are men and 20% are women. Here's our probability tree with the delinquent and not delinquent, and each of our resulting probabilities for each branch of the tree. So notice that if I look at those 2 branches and I add up their probabilities, it makes 80%. Well, those 2 branches are all of the branches where the account belonged to a male, which was 80%. So that makes sense. What I want to figure out now is what's the probability that an account will be delinquent. Now notice that that's not a branch because it doesn't take into account the male-female aspect. It's just any delinquent account. So I look through my sample space. Here's a delinquent account, and there's an account that's delinquent. And I would sum those 2 probabilities. So there's a 0.128 probability that it was a male account and delinquent, combined with a 0.01 probability it was a female and delinquent. Add those together, I get 0.138. So about 14% of the accounts in the store are delinquent. Okay, knowing that, let's find the probability that an account is not delinquent. I can do that 2 different ways. I could look for all the branches where it's not delinquent and add up those probabilities. That would be 0.672 plus 0.19. It's 0.862, or 86.2%. And that strategy works. It's a little bit easier, in my opinion, that the probability that it's not delinquent would be 100% of the accounts, subtract the 13.8% that are delinquent, because an account is either delinquent or it's not. That would also give me the 86.2%. Now finally, I want to have the probability that the account was owned by a man given that the account was a delinquent account. So this kind of given, it has the effect of reducing the sample space so that you're only looking at the part of the sample space that was delinquent accounts. So it's like taking your probability tree and erasing any part of it that wasn't delinquent. So you're going to restrict your vision to only the delinquent accounts. So now in my total sample space, there's 13.8% of my accounts, so it's 0.138 between the two. What's the probability that it's a male? So a success would be that it's a male account. That's this one. It'd be 0.128 out of 0.138. That's 0.9275. I could also ask what's the probability that it's a female given the account was delinquent. So I restrict the sample space to only the delinquent accounts, and that's the combined 0.138 probability. And then probability of a female is 0.01, which is 0.0725. Okay, we'll do one more example and then we'll send you to your homework. Use a probability tree to find probabilities for this. A bag contains 13 blue balls, 7 red balls, so 20 altogether. 2 balls are drawn at random and the first ball is replaced before the second is drawn. Okay, let's get our probability tree. We could have red and blue. Probability of red, 7 out of 20, and blue is 13 out of 20. After the first draw, we have a second one, which could either be red or blue. Red is still 7 out of 20, blue is still 13 out of 20, with replacement. Second draw, either red or blue. Red, 7 out of 20, blue, 13 out of 20. So this first branch would be red, red. That's 7 out of 20 times 7 out of 20, 49 out of 400. Second branch is done similarly. Okay, so constructing the probability tree gives us these 4 branches with their corresponding probabilities. What's the probability the first ball is red or the second ball is blue? So a success is either a red ball first, those two, or the second ball is blue, this one. Those 3 probabilities added together makes 309 out of 400. Okay, now the second question, that the first ball is red given that the second ball is blue. So given that the second ball is blue means we have to take our sample space and throw out everything except where the second ball is blue. That's this one and this one. And now the probability of red given blue on the second. It's the number of ways, the number of successes, of the total outcomes. Success would be red on the first ball. That's 91 out of 400. Out of total outcomes is the combined probability here. 91 out of 400 plus 169 out of 400. That's 91 out of 400 over 260 out of 400, which makes 91 out of 260. Okay, go in and try your homework, and hopefully between the lecture and the homework videos you'll be able to get all your homework done. If not, send me your questions.